Hi everyone, welcome back to the Technion's ECE Deep Learning course. I'm Tal, and in this video we're going to continue our discussion on sequence modeling and shift our attention to, well, the attention mechanism. And the main idea is that instead of recurrent processing of the input sequence, we will look at the entire sequence at once, which will enable us to process all the input tokens in parallel. There are many advantages to doing this, and we will cover them in this tutorial. So let's start. Okay. So far we have processed the inputs sequentially. This is the recurrence mechanism, which has led to several issues. The question we're going to ask here is, can we process sequences differently? And here is the idea. We can look at all the different tokens or words at the same time and learn to pay attention, give each token a weight to the correct one depending on the task at hand. So basically we are going to learn some weights. Now, the attention can be thought of as a generalized pooling method. That means we are going to extract features from sequences, and this is what we are interested in. We want to extract features from text, for example. And the idea is to use something called bias alignment over the input. And we are going to formalize the terms of the attention layer. It's going to be a layer, a neural network layer, like we've done so far. And we are going to call the input to an attention layer a query, and we will also have key and value, and we will see how everything is integrated together. Now, there are two main types of attention. One is called self-attention, and the other is called cross-attention. And in each type, we can also define soft attention or hard attention. Now, in this tutorial, we are going to focus on self-attention and, of course, soft attention. And soft attention basically means we're going to use softmax instead of argmax. And we need everything to be differentiable, and this is why we're going to use a continuous function. Now, you can think of self-attention as just extracting features from the same sequence. And cross-attention will be, we'll ask the question, how do we extract features from two different sequences? So for example, in machine translation, we will have sentences from two different languages, and we want to understand how we model the relations between these two sequences, and we will use something called cross-attention, but we'll talk about it a bit later. Okay. So the idea is that in self-attention, we have a sequence of tokens, or in this case, the sentence, hello, I love you. And we want to compute some weight matrix that will help us create our feature representation. And in this case, you can see that basically we model the relations between every word in the sentence. And not surprisingly, on the diagonal, we have the relation between the word and itself, right? So so the main diagonal has the highest weight. But we can also see the relations between different words. So we can see that I and love, so this cell right here, have stronger connectivity, than I and hello, for example. Okay. And of course, this can be thought of. So we are going to have this attention matrix, but this can be also thought as like a connected graph with weights. And of course, it's undirected because we did not define the order. So if we scramble the order of the words, we will get the same values for the same inputs. Now, this is an important property of attention, which is permutation invariance, and we will see how we induce the order of the input inside the attention mechanism, but we'll see that later. And remember that it's important to have the order modeled as well, because otherwise the sentence may lose its meaning. So if you scramble the words, the sentence will be different and might have no meaning at all. Okay, so let's formalize this a bit. So we are going to have our inputs sequence. So our sequence will be of length t, and we're an embedding dimension of each token, which is d. And of course, we can represent it as a matrix, and you will see soon that the tensors have different shapes, so just like we did in the previous tutorial. Now, the idea is that for each input embedding, we are going to output a feature vector age, which is weighted weighted linear combination of the other input tokens. So for each token, we will have this representation, and we're going to learn these weights, which are denoted by alphas. Now, of course, we can stack everything to a vector and a matrix later. So basically, for each input, we are going to have a feature representation. Now, what are these alphas? Though these are weights, and they should sum to 1. And this helps us define our attention and soft attention. So if the alpha is a one-hot vector, that means that we have only one as input. It's like a selector. Then we just select the correct word, right? So this means that the hidden representation is just a selection of a token. And of course, this is not really differentiable. There are ways to differentiate this, but we are actually going to use this soft attention. And in soft attention, we just use softmax. So basically, all the alphas sum to 1, and they are continuous numbers. Okay, cool. Now, how do we get these alphas? So how do we compute these weights? So the idea is that we are going to use orientation or similarity, and we are going to take our input, so our input sequence x, and we're going to multiply it by every other input, so xi. And this means we are actually calculating the similarity between the embeddings, right? Now, the difference between hard attention and soft attention is how we pull these scores, and soft attention just applies our softmax. Okay, so just numbers that sum to 1. Okay, now this is usually called also scores, and basically this scalar product tells us how aligned or similar two vectors, two embeddings are. And of course, this is going to be learned, so the input is going to be features that are learned, and everything can be trained with backpropagation. Okay. Now, of course, we can just do this in matrix form, so xtx, and basically this means that the attention will be a matrix t by t. So for each input token, we will have a weight. So this is the attention matrix, and you can see that the dimension is the sequence length and not the embedding dimension, okay? Because we calculate similarity between the entire token. Okay, so I'm going to show you an example of what it looks like when we put attention inside a neural network. And in this example, we operate on a sequence of part words, so tokens are part words. And we have this sentence: the animal didn't cross the street because it was too tired. And when the task can be, for example, next road prediction or classification. And basically, we are going to learn these weights, alpha A, right? And what we can see is that like in convolution, we are going to have, so remember in convolution, we put multiple filters in the same layer, right? So like we do there, here we are going to call this heads. So each head operates on different part of the input, and in each attention layer, we're going to have multiple heads, which attends to different part of the input. So here we can see two heads. So we have the orange head and the green head, and we can see the different heads learn different connectivities. So for the orange head, we can see the word "it" has strong connectivity with the phrase "the animal," and this is not surprising because it refers to the animal, right? And another head refers to has strong connectivity with tired, which is the verb. So who was tired? It, and it is the animal. So basically, we can understand the attention as some correlation and learn some features to represent the similarity between and the connectivity between entries in the sequence, right? Great. So we can see how we can extract features, and this is a great mechanism. And we're now going to formalize this in what we call a key value mechanism. And the way we are going to do this is we are going to have a running example, which is called the lasagna recipe. Okay, so let's go over it. Okay. So now that we understand how we can calculate scores based on similarity, which is a very simple equation, we now apply it in a key value fashion. And the idea is that we have some cache or dictionary, and basically in the literature, a key value is a mechanism to store and retrieve, basically managing a dictionary or hash table. But we're going to demonstrate it in a very simple way, which is called, and in this imaginative example, we're going to use it through this entire tutorial. It's called the lasagna example and the lasagna recipe example. So we need to define query, key, and value. So query, you can think about it as like you are looking for a recipe and you look for some title. So for example, query would be lasagna. You want to look in the recipe book and you will look for lasagna. So query, let's go over it. So say we wanted to find a recipe to make lasagna. We have a recipe book and we search for lasagna. This is the query. So this is the input to the attention layer. Now we have our dictionary, and our dictionary is composed of keys and values. So keys can be the titles of the recipes in the book, right? And we are going to compare our query to the keys. So basically we calculate the similarity of our query with each entry in the dictionary and with each key. Okay, and we take the maximum matching score between the query and all the keys. And once we have this correlation, these scores, we can actually retrieve the correct recipe, which is the value. So the value is the actual content of the recipe. So basically, key and values are connected because keys help us retrieve the correct values, right? So basically, when we compare K and Q, okay, we can do this, we calculate the scores and we can take the argmax or the softmax. And if you use the argmax, we just retrieve a single recipe. And if we use the softmax, we get a mixture of recipes, right? And this is how you end up basically with a pineapple pizza, right? Because you mixed some things from the recipe book. Now, this example, which I really like, is from NYU, and we will use it throughout this tutorial. Right, so this illustration here shows you what it means to have query, key, and values. So basically, we are going to have attention, so similarity between queries and keys, and then we retrieve the values by using these weights, which was calculated using the attention, and we retrieve the relevant information. Now, this is implemented as follows. So this is the attention formula, which is a very simple formula, but it revolutionized the field. Okay, so this simple equation led to really important progress in our machine learning field. So what is an attention layer? So the inputs to the attention layer is query, key, and values. So we need to define the dictionary, which is defined by keys and values, and we have our queries, which are queries to the attention layer, right? So the input. And the idea is that we want to go from our query to the values, right? So the attention formula is as follows. So we have our queries, we have our keys, we compare them with this product similarity, right? We also have some normalization by the dimension of the embedding. That's not important right now, but it's super important for the implementation. And then we apply softmax to calculate these weights, and then we retrieve the values, okay, corresponding to the inputs in the attention matrix. Okay, so let's see how it works in practice and how we implement it, right? So in our case, we are going to implement self-attention. So basically, we are interested in getting features from a single sequence, right? So we are going to denote the vectors Q and K and V as the query, key, and value, respectively, and their corresponding learnable parameters matrices. So for each Q, K, and V, we actually create them using projection matrices WK, WQ, WK, and WV, and basically they are used to project our input embedding. So we will give this the attention layer our input embeddings. Then we are going to project these embeddings. So each entry in the embedding in the input sequence, which is an embedding, is projected to query, key, and value, right? And then we get the projections, which are QKV, and then we are going to apply the attention formula, right? So a couple of things to note here. So we also usually don't include nonlinearities or biases inside these projections. So it's going to be an n-end of linear layer, but without any activations following it. And also usually we don't include the bias because it's completely based on our orientation. So we want a linear projection. Now, in order to compare the query against all the possible keys, we must have the same dimensionality, right? So basically the projections of Q and K must have the same dimensionality because we take the dot product. So we need them to be of the same dimension. Now, the value itself, so if Q and K are the titles of the recipe, of course they need to match in dimension. Now the actual content, the value does not have to be of the same dimension, so the actual recipe can be some other dimension, so dv. But in our case, and for simplicity, we are going just to take that every projection is of the same dimension d, and this is what we actually also use in practice. So in practice, we also take the same dimensions for the Q, K, and V, right? But in theory, you can give the value a different dimensions, and there are several applications that use different dimensions. But for the simple case, we don't need it. Okay. Now, of course, we can actually do this in parallel. So we don't care about the order at this point. We just care about projecting all of the input embeddings to Q, K, and V. So of course we can define the matrix Q, K, and V, which is just D by T, because for each input in the sequence we get a projection. And this is implemented in parallel. We can do this in PyTorch really easily. And this is why we don't need to wait for the previous input. So we look at the entire sequence at once. So this is an advantage because in RNN, if you recall, we need to wait for the previous inputs to be processed so that we can process the current input. Okay, now that we have the projections, we just calculate the attention formula, right? So the dot product is just going to give us the attention matrix, which is going to be of the dimension of the sequence length, right? And then we are going to multiply it by our projection of the value and to create our hidden representation age, okay, which is just a feature representation, and we can use it for any downstream task. So if you want to do classification, you can take this age and then just apply fully connected, just like we did in the RNN example, right? And of course, the dimension is maintained. So we have D by T, where D is just the dimension of the values. So another illustration for this. So we have our input sequence x1 to x4. So we have 4 entries in the sequence. For each entry, we have an embedding, right? So these columns. And then we perform the projection. So we have the projections matrices, right? And create the Q, K, and V. And then we just apply the attention formula, which is very simple. And don't forget, we need to scale the dot product by the dimension, and it's very important for the implementation because everything needs to be scaled. Right. Another illustration for this. So just a different colors, right? Same. Now pay attention that you need to you need to be aware of the dimensions. So if it's D by T or T by D, this will define how you perform the dot product. So KTQ or QKT, depending on the shape. Okay, cool. Now, for implementation, we can actually, there are several implementations that actually stack everything to a single matrix. So WQ, WK, and WV are stacked, and we have some single matrix that is that its dimension is 3D. And this is just to speed things up, nothing too important. Now, as I've mentioned before, like we did in convolution, where we had multiple filters per convolution layer, we can have multiple heads per attention layer. Basically, the idea is that each head is going to attend to a different part of the input. So this is illustrated right here. So after we perform the projections, we just separate our input, our vectors, to multiple heads. So you can see that the first head operates on the first 2 dimensions, and the second head on the following 2, and so on. Right. So basically, this embedding dimension should be divisible, but by the number of heads. And the idea is that if we compare it to the lasagna recipe example, is that instead of looking inside one recipe book, we are going to take we are going to look in multiple dictionaries or multiple recipe books, right? So just to add expressiveness to the network. And this is very similar to what we saw in convolution, but in convolution where filters operated on the entire input, this is very similar to something called group convolution, where several filters operated on only part of the inputs and the other on the second part. So in this example, you can see that the input is divided to two parts, and the first part is convoluted with the first set of filters, and the second one, so here it goes again. So we have the first set of filters, the first 4 operate on this first part of the input, and the other 4 operate on the second part of the input. And this is the idea of adds. So we have adds for different part of the inputs, and we'll see how we implement it. So this is going to be a hyperparameter, how many heads you want, and just like the way you thought about how many filters you put inside a convolutional layer, right? So let's implement this and do this step by step, right? And I want you to see that it's quite simple. But at this point, you need to remember that while we can do this, we can do everything in parallel, because nothing here was dependent on the previous input or something like that. Everything is done in parallel. In sentences, in NLP usually, or other types of sequences, for example, time series, then we actually care about the order. And this attention operation is permutation invariant, so it doesn't care. Like, you calculated the scores, but you never treated the input as a series, so that one comes after the previous one. So you need to provide this information to the attention layer, like explicitly, in order to actually be able to model this sequence as an ordered sequence. So in NLP, we care about the order of the words in the sentence, and this is why we need to give every input some representation of where is its position inside the sequence, because it's important to understand for the understanding of the sentence. But we'll see how we do it later. So multi-head attention, let's see how we implement it. So everything is every neural network inherits from an end.model. This is nothing new. We have the init, so and the init where we define our blocks, and we have other auxiliary functions, and we have the forward. Now what I want to do is start actually from the forward, because we need to understand how everything is processed, and then we'll see what we need for each part. Okay. So the input to the attention layer is the query key and values embeddings, right? In the case of self-attention, these three are the same input, okay? In cross-attention, then XQ is different, and XQ and V are different. So for example, in machine translation, and you want to implement cross-attention, the input for the query is a sentence from one language, and the input from the K and V are the second language, the second sentence from a different language. But in our case, self-attention, so these are all the same. Now, what shape of tensor it expects to get? So it should be batch size, sequence length, embedding dimension, right? Nothing new. Now we are going to get our projections, so Q, K, and V. So you can see that we just apply the projections Q, K, and V, right? Now let's see how they are defined. So they are just linear layers, right? That takes us from the embedding dimension to this D. Now in this case, dV is equal to dq and dk, nothing surprising. And sometimes, well, it's usually like this, so the bias are turned off because we only care about the orientation. But this is not usually the case. Sometimes you can just turn them on and everything still works, right? Okay. So we have our projections, and now we are going to split our Q, K, and V to heads. So we said that each head operates on different part of the input. So you can see that when we initialize the attention layer, then there is a test here to make sure that the D that you chose, the embedding dimension, is divisible by the number of heads. So this is super critical. So pay attention to this. Okay, so the next thing is just to split the projection to heads. So different heads, different attention, right? So this is very simple function. Just change this the way this tensor is viewed, just the shape of the tensor. And this line will work. This line will work because we had this check here when we initialized that we can actually change the shape because the model is divisible by the number of heads. Right. So after we split it to heads, we now perform the dot product attention. So the input to the attention formula is just Q, K, and V, and you can see the formula here. So it's just doing the very simple equations that we saw above. So we scale by the embedding dimension, we calculate the QKT, right? And then we get the scores, and now we apply softmax. So we are doing soft attention, right? So basically we have the scores, which are just sum to 1. We also apply dropout optionally, right? And then we create the hidden representation, which is just taking the weights and multiplying them by our projections of the values, right? And you can see that the dimension here is batch size over heads over Q over dimension per head. Now, this attention was calculated per head. So each head had its own calculation of the formula we saw above, right? So this is why the dimension here is the decay, which is the number the effective dimension when we calculate we divide the d by the number of heads, right? And we also return the matrix attentions, the attention matrix. So basically, if you want to plot and see this drawing that we saw above, then you can actually plot these numbers and see the connectivity. And this is something people do. It's nice visualization to see what the attention learned. So once we have this age, then we just change the shape to collect all the information from all the heads. So basically return to the original dimension. And then we have a final linear layer. So just another, just to add expressivity to the network. So just another linear layer. And then we have our output from the attention layer. Okay, so it's quite simple, right? Nothing here too bombastic. So let's see that it works. So what we're going to do, we're going to define K, V, and Q, and we are going to see that our function here, this scale dot attention, works as we hope for. So the idea is that we are going to have our titles of recipe, keys, right? So these are the keys, and this is the content of the recipes. So we have these values, and now we are going to define some query, and our query is 0, 10, 0. So this means we ask for the second recipe, right? So if the attention mechanism, if the scale product attention works, then we should be able to retrieve this recipe, right? The second recipe. So let's see that it works, right? So this function is just applying the scale product attention, and what we can see is that the attention weights are 0, 1, 0, 0, right? And this means that our alignment works, our scores similarity works, and the output is 10, 0, 0, which is the second recipe, right? So it works. Nice. Right. So the attention mechanism works. And what we're going to do now is build something called the transformer. So the transformer is a very popular architecture, which is purely based on attention operations, but we add some stuff to make it actually work. And one super important thing that we need to consider is the order in the sequence. So when we want to operate on series that the order has some importance. So for example, in NLP, the order of the words in the sentence, they are important, or for example, in stocks prediction, we care about the past and we need to know what came before what, right? So, and this is what we're going to do. We are going to actually implement this and see what other, additional components we need in order to achieve this. So the transformer is an attention-based encoder-decoder architecture that aims to combine the advantages from MLPs and RNNs. And let's see how we do it. And the idea is that we are going to look at the entire sequence at once, so we achieve parallelization, right? And this can make the training faster, and also we don't need to think about the memory or the hidden state or something like that. Right. Now, one thing we need to do, so in RNNs, because we waited for the previous input to be processed, then we implicitly included the position information already because we waited. So the input was processed in recurrence, right? So we actually already induced the positions of the sequence. But here in Transformer, in attention, we actually look at everything at once. So we need to explicitly input the positional encoding of the entries in the sequence. So it's important to know that the word house was the third word and not the first one, right? So we need to add this information to the attention, and we'll see how we do this. And another important thing is normalization. So because we use this orientation operations, it's important to have normalized values for the features. So we will use layer normalization, and we will talk about normalizations in general in the next tutorial. Okay, so there are three main stages. So the input stage, and we have blocks. So just like convolutional blocks, we're going to have transformer blocks, with just attention blocks, and of course each is initialized differently. Now, when we say transformer, we usually mean an encoder-decoder architecture, but we don't always need to use an encoder-decoder. There are several applications where we only need to use a transformer encoder. There are several cases where we only need a transformer decoder, and there are certain cases where we actually need both. So let's see some examples. So for classification, for example, sentiment analysis, what we're going to do in this tutorial, we may just use a transformer encoder because we want to take a sequence, encode some features, and then give it to a classification network, right? Now, if we actually don't do classification, but we do a next token prediction, for example, language modeling, so like GPT, we may just use a transformer decoder. So basically, it's very similar to the encoder, but with the additional masking. So we need to mask the input, and this is a bit advanced, so we can talk about this later. And finally, when we have tasks that are required that require that we have cross attention between two different sequences. So for example, sequence to sequence in machine translation, then we need both encoder and decoder, and we will have cross attention between the output of the encoder and the input of the decoder. So we will also see an example for that later. And in general, this is the structure of the transformer. We're going to have our inputs, we're going to give them the embeddings, and then we are going to encode the positional information of each entry. This is important for sequences where the order matters. And then we're going to have an attention layer, so basically just multi-add attention with skip connections and normalizations. And we also have MLP at the end, nothing surprising. The architecture of the decoder is similar, but instead of self-attention here, we are going to do cross-attention between the outputs of the encoder and the inputs of the decoder. So you can think about it like the input here is an English sentence, and the output here, what you want to actually model. Then, for example, French sentence in French. So we will have our French embeddings right here, and we're going to do cross-attention between them and actually retrieve the correct output. Okay, so in this tutorial, we're going to focus on the encoder, and then we have some resources to show you how to use a decoder. Okay, so the idea is basically depicted in this illustration. It's not that complicated, and you see that the implementation is very short. So we are going to have our sequence. It's going to get an embedding, right? And then we are going to provide it with positional encoding. So we need to know that thinking is the first word in the sequence, and that machines is the second word. And we're just going to encode this information explicitly, because in attention, which is a permutation invariant operation, the order does not matter in order to call it, because it's just similarity, so it doesn't care about the order. Then we're going to do self-attention, so just extract these features. We are then going to use layer normalization and just skip connection, okay? So we'll see how it's implemented, quite simple, and the skip connection helps us with the gradient propagation. And then we are going to have MLP and another skip connection. So very simple. So let's see how we implement every part of this decoder, and then it will be very trivial just to stack many layers of encoder, where each layer is just like this. Okay, so let's see how we implement every component, right? So I'll just note, and we will see this in the third part of the sequence tutorial, that here we can see that the layer norm is after the attention, but now it's very common to use the layer norm before the attention, though this architecture is called post norm, and what we usually do today is pre-norm. So we normalize before we input the attention there. But let's wait for it. So let's start with a simple component, which is just the MLP at the end. So the MLP at the end, nothing new here, right? It's usually implemented like this. So we have our first fully connected, we have activation, we then have another linear layer, and we usually also add some dropout. So very simple. Now, one thing to note here is that we operate on the last dimension, right? So in PyTorch, the nn.linear, it doesn't care that your tensor is 4D or 3D, it just operates on the last dimension. So this MLP is shared between all the embeddings, right? Because this same MLP works or operates on every entry in the sequence. So it's the same, so the weights are shared. We just extract the information from each entry in the sequence, right? So here's an example. So we have this input tensor, which is patch size of 2, right? Sequence length of 3 and embedding dimension of 4. When we give it to our feed-forward network, our MLP, the output is the same because it's usually structured like we have a hidden demultiplier where we just increase the dimension by 4 and then we return to the original dimension, right? So we have like a network that grows in the middle and then goes back to the original size. And you can see here that the output dimension is the same, right? So we have a sequence of 4. We have a dimension, we have an embedding dimension of 4, and we have three inputs in the sequence, right? Cool. So let's talk about the more interesting stuff, is how we encode positional information in this neural network. So unlike the recurrent layer, both the multi-head attention layer and the position-wise feed-forward network here, this one, they compute the output of each item in the sequence independently, right? They operate on each entry in the sequence, and this means that we don't care about the past. So the positional information, we need to actually input it in explicitly. Now, when we do it, we can actually parallelize the computation. This is very fast, especially when implemented on modern GPUs. But we fail to capture the positional information. So we need to know the order of the words in the sentence. So the way we are going to do this, we are going to use something positional encoding, and this is used to maintain the positional information of the input sequence. Right, so we are going to encode the explicit position. So we need to, for each embedding, we are going to add to it its position in the sequence. So the first word is going to get encoding. That means I am the first word, right? And the original transformer, the vanilla transformer, they used sine cosinus functions to add this information. And people usually don't do this today anymore, and they use just learn embeddings. I'll show you in a bit how it looks like, but let's cover it because it can actually help us understand what is happening. So the idea is that we have, here is our input sequence metric. So remember, we have the sequence length and we have the embedding size, right? So each cell here is going to get a unique indicator of its position. And we are going to encode the position in the sequence and the position in the embedding dimension. So the idea is that the even positions are going to be encoded with sinus, with the sine, right? And the other with the cosine, the odd positions with the cosine. And we just have this number, which is very large, and it's usually enough, right? And we are going to do this with addition. So if you were thinking that maybe we can encode this with concatenation or something like that, this is what works the best. Just adding the positional encoding. So basically, you just add the bias. You move each entry here by its position. So we can see what it looks like. So before I'll show you the implementation, we can see here what's happening. So we have a sequence of length 100, and we have for each, so the dimension, so the embedding dimension is 20, and we can see that every position in this matrix gets a unique indicator, unique value. So we can see here that word number 20 in the sequence gets different values for its embedding dimension. So for the fifth dimension, there is -1, which is added. And for the fourth dimension, we have 0. And similarly for the others, right? So each position in this matrix gets a unique value. And this is important because it helps the transformer or the attention matrix embed the positional information. So basically, when you do this, you tell your attention that this entry is positioned like this in the sequence, right? So it's very easy. It's very simple to implement. So it's just we implement it as a layer, right? We need to give it the embedding dimensions, and the maximum length of the sequence. So this is the number right here, and usually 10,000 is enough, but in most cases we don't need this much, this large sequence. So you can see here that when we get an input x, we just give it so this matrix is deterministic, right? We can pre-calculate it if we use the sine and cosine, and we just take the correct number. So you can see how we create it. It's quite simple. And when we perform the forward, then we take our input and just add we just add the positional information. Now, a much simpler and more common approach today is just, instead of defining this positional before training, we can actually have a learned positional information. So the idea is that we are going to initialize some weights for each position, right? So we have our maximum length of the sequences and the number of embedding them and the embedding dimension. And basically this can be learned with back propagation. So just you add for each x, you add these embeddings. And this is much simpler and works really good. So I recommend starting with this actually, but it's important to know what the original transformer used. Okay. So our embedding layer is going to do two things. First, so the embedding layer is going to get the tokens, okay, and then we use nn.embedding to get the embedding, right? So this is also learned, and after that we are going to add to each embedding the positional information. So you can see that the forward here is just first get tokens to embeddings, then add positional information, and we also use normalization here. It's not that important, and we return the embeddings. Cool. So maybe this is the most crucial component besides the attention, because we need to encode the positional information. Right. So our encoder layer is going to be very simple. So you can see that we need to choose number of adds, the multiplication of the MLP, and dropout. So you can see that the encoder layer is doing just the drawing above. So this one, it's very simple, right? So let's look at the forward. So the first thing we do is we get our x's, right? And then we apply multi-add attention, right? So just the same inputs. Then we apply, then we do the skip connection and apply layer. This is the first part, and the second part is just applying the MLP, and then again skip connection and layer norm. So very simple. Now, as I've told you before, this is called post norm, and actually it's common now to use pre-norm. So we apply the layer norm first on X, then we calculate the attention, then we do the skip connection. I'll show you in the third part of this tutorial how we implement pre-norm, and this is pretty easy and works usually about the same or a bit better. Okay, so finally, we have an encoder layer for attention. We will now build the transformer encoder, so we need to tell it how many layers we want and how many and everything else that we need to input. So first we have the embedding, right? So this is the embedding layer. Then we have a sequence of attention of encoder layers, right? And that's about it. So first we get the tokens, we convert them to embeddings and add the positional encodings, and then we just apply the sequence of encoding of attention layers. So typical numbers for the number of layers and number of heads. So usually number of heads is 4, 8, 12, 16, things like that. And the number of layers, again, 2, 4, 6, things, numbers like that. Finally, let's use it for classification. So let's use a transformer encoder for classification. So remember, we are working with the IMDB dataset. So we are going to have an encoder. And finally, we are going to have a projection layer that outputs the number of answers or number of classes, right? And this is how it works. So first we get our tokens, right? We apply the transformer encoder. We get something like batch size, sequence length, and embedding dimension. And now we need to pull it because we only care about, we want to just classify. So we usually take the last one, take the maximum or the average. Everything works. And then we apply the final fully connected layer to predict the number of answers. So we did something similar with the RNN. In the RNN, we took the final Elm tree in the sequence, but there are other pooling options. So just pick one that works the best. In this case, we pick the max. Okay, so IMDB, we can see the transformer encoder here. The training looks very much the same. So just remember to put it in training mode because we have dropout, right? And now the training looks the same. We calculate the accuracy, and hopefully we can see that our accuracy goes up, right? That's good. And final accuracy is about 83% for the IMDB datasets. Okay, that's cool. You can use it, of course, and you can see, we will see later that we actually have a transformer already in PyTorch with all the nice optimizations and tricks to make it work better. Now for the decoder. So I'll shortly cover the decoder part. And the idea is that when coupled with an encoder, it's usually for sequence-to-sequence tasks, so for example, machine translation. And the idea is that we are going to have an encoder, which is just what we implemented. And then we are going to take the output embeddings, and we are going to use it in as inputs as cross-attention to something similar to the encoder, which is called the decoder. And the input the decoders are embedding from the other sequence. So in machine translation, the entries from the second language, right? And the idea is that from cross-attention, we are actually going to use this input as the input to the input here is going to be the query. So the second language is going to be the query, and the dictionary is going to be keys and values from the encoder, right? And basically, the idea is that we are going to use some causal masking here to make it autoregressive. So we can see what happens at inference time. So we have the input from the first language. In this case, I think it's French. And we are going to get the encoding, and they are going to be used as keys and values for the cross-attention in the decoder. And in the decoder, we are going to do this autoregressively at inference time. At training time, we can do this in parallel because we actually have the target sentence. So this is called teacher forcing at training time when we input the ground truth values. So let's see what happens in inference. So the first thing we do is we decode the I. Then we get the embedding, we decode the next word. So this is next word prediction. And each time we have cross-attention with the original sentence from the first language. So we can see how we auto-regressively predict the next word. And we only do this auto-regressive decoding at inference time, because at inference time we don't know the output. We want to decode it. But at train time we have pairs of sentences from different languages, so we actually can do this in parallel. So we can just use exactly like we did in the encoder. Right. So to summarize, the transformer looks something like this. We need to think whether our task requires us to use both encoder and decoder. And for each, so the basic components are the attention and the embeddings, and we also have the skip connections, layer normalization, and the final MLP. So that's about it. Nothing too fancy, just the way we connect all these components. Now, here we implemented everything from scratch, but we actually have everything implemented in PyTorch. So we have nn.transformer, and you can see all the parameters here. So if you want to use, for example, pre-norm instead of post-norm, then norm first equals true, and you can choose the activation. But basically, and it's also optimized for speed. So basically, it's better to use what's already implemented because it's very optimized and will work faster than your implementation probably. But we also can use just transformer encoder, just transformer decoder. Everything is under the documentation. Take a look if you want to use transformers. Now, the nice thing about transformers is that when you give them a lot of data and you use a large model usually, then you can get really nice and really good performance in downstream tasks. And the idea is that we can now do some pre-training. So basically, we can pre-train transformers to give us embeddings or to give us representations, and we can use these representations in downstream tasks. So one of the popular examples is BERT. So BERT is bidirectional encoder representation from transformer, and the idea is that we are going to take a very large corpus of text data, and we're going to learn embeddings. And the way we do this is with some unsupervised tasks that we define, and I'll show you, or self-supervised, and I'll show you in the coming tutorials how we actually what we actually do in BERT. Another application is, so BERT is just a transformer encoder, and we also have just a transformer decoder, so GPT, generative pre-trained transformer, and GPT is just pre-trained to predict the next word, right? So basically, it's a transformer decoder, so no need for an encoder because we are still doing self-attention because we only care about predicting the next word in the same sentence, right? So we can just use a transformer decoder. Now, you are all familiar with ChatGPT, and the main idea is this autoregressive prediction, and just a transformer that is pre-trained to predict the next word. Now, there are many applications for this, right? So you can see here that we have a transformer running in the background, and all these autocomplete features are using transformers. So all this next word prediction is just a transformer operating in the background. Now, how can we access all these pre-trained models? So there is a company called Hugging Face, which collects all these pre-trained models, and you can just download them with a couple of lines of codes, and they have nice API, and basically you can use all the latest models. So it's not only for language but also for vision and video and other stuff. So take a look at the Hugging Face hub. And they have really nice API, and it's free, of course, for personal users. And you can see what models you can use, and of course, feel free to use them in your projects. Okay, now finally, I'll just say that while we talked about sequences in the form of words, we can actually think about images as sequences by separating them to patches. So each patch can be a token. And this is a family of models that is called Vision Transformer. Okay, so it's also a new or a recent progress in this field. And basically the idea is that if you compare to CNNs, then if you have enough data and use a large enough model, then Vision Transformers can be competitive with CNNs. But if you have small scale data and things like that, CNNs still work the best and converge much faster. But there are pre-trained Vision Transformers or ViTs that you can use, and they give you features, and you can take them to downstream tasks or classification and things like that. So here is an example how we create tokens for an image. So just give it your image and the size of patch, and now each patch will be a token in the sequence. And of course, we are going to have positional embeddings, but it's going to be 2D. So we are going to embed the pixel positions, and it's 2D because we have 2 dimensions. Right. Okay. So this is it for this part of the tutorial. In the next tutorial, I'm going to tell you about recent advancements in the transformer literature, and basically how we can make transformers even better and what actually happens today mostly. And there is a lot to cover, so I won't be covering everything, but I'll give you resources to where you can keep up to date, where you can stay up to date. And this is what we'll do in the next tutorial. So thank you for watching, and I will see you next time.